Hey everyone, this is Paul from Signal Processing with Paul, and down here is my lazy dog Sprocket. In this video, I want to help explain why the Fourier transform will help you be almost as lazy as Sprocket. So what do I mean when I say the Fourier transform allows you to be lazy? Well, let's start with an analogy. Suppose you're here on one side of the river and you want to get to the other side of the river. And if I told you you're here, you also know that there are actually some trees around. So here's a tree and here's another tree. And you know that if you spend some time, you could chop down these trees and maybe make some logs and maybe eventually build a bridge and, lay those logs across the river and build a bridge. But, that's a solution. That could work. But what if I told you somewhere downstream, if you just maybe 200 feet downstream, there's already a bridge made. So as a result, all you have to do is start from where you are, walk down the river to where the bridge is, then just walk yourself across the bridge to the other side of the river, and then walk yourself back up the river to the place you want to go. In other words, rather than have to build your own bridge from where you are, you can just walk down where there's already a bridge made and simply walk across the bridge. This is basically what the Fourier transform allows you to do. Now, one of the examples that you often see is with linear differential equations. And one of the things you hear all the time is the Fourier transform turns linear differential equations into algebraic equations, which makes them easier to solve. But I want to explore why that's the case. So suppose this is a really famous one. This is the Euler-Cauchy equation. This is x squared d squared y dx squared minus 2x dy dx plus 5y equals ln squared of x minus ln of x. Ugh, nasty, right? Why solve this directly when there's a way you can make this equation much easier to solve by looking at it in a different way, and then you can just transform it back once you've solved the equation into a way that's really easy. And this is what the Fourier transform allows you to do. When I take the Fourier transform, which is from minus infinity to infinity of f of x e to the minus j 2 pi fx dx, what I'm doing is I'm writing my function as basically a sum of these basis functions that are complex exponentials. Now, what's so special about the complex exponential? Well, let's take a moment here to think about what's going on. The equation e to the theta x, it's a very special type of function. When I hit it with the derivative, d dx, what do I get? I get theta times e to the theta x. And when I take an integral, what do I get? I get 1 over theta e to the theta x. Now, if you look at this and you think about it, this is the reason that the Fourier transform turns differential equations that are linear into algebraic equations, because any derivative, you just hit it with basically a multiple of your original function. And every integral, you hit it with basically another multiple of your function. In other words, you take another derivative, you get, boom, theta squared e to the theta x. Take another integral, 1 over theta squared on the bottom, e to the theta x. As a result, this is the reason this works is because the complex exponential is the eigenfunction of linear time invariant systems. So what do we mean by eigenfunction? Well, if you remember from linear algebra, the eigenvector of a matrix, so if I have AX, if X is an eigenvector, then what you get by hitting it with A, so this is if X is an eigenvector of the matrix A, then all you get is a scaled version of your original vector. And in this case, if we consider our basically our matrix to be the set of complex or basically linear time invariant systems, then notice how the eigenfunction of the derivative operator is the exponential. Because what do I get when I take the derivative? I get a scalar multiple. Here is the eigenvalue of the differential operator. And likewise, when I take an integral, well, what do I get? I get a eigenvalue times the eigenvector. So this is why we like writing our function in terms of complex exponentials. Rather than writing our function as a function of time, if we can write our function by a function of frequency, where each frequency is basically its own special complex exponential, now taking derivatives and integrals is really easy. This is what allows us to turn our differential equation into an algebraic equation. So you come over here, and now we get basically t f of f, or maybe you could say y, and then all we do, convert it back into the time domain using the inverse Fourier transform, and now we've gotten to where we want to go without having to do all the work. In other words, we've been able to be lazy. So hopefully you found this video helpful for motivating why the Fourier transform is so important. If you want to learn more, I know Ian has a bunch of great videos on the Fourier transform, and I may be doing some, but I don't want to step on his toes, so I may do something a little different, like looking at this from a more linear algebra sort of perspective. But anyway, I hope you found this video helpful, and yeah, thanks for watching.